So today we have Matt Robinson. He is a program manager at ROS-Industrial Consortium Americas. I saw his talk at Robotics Industrial Conference that happened last year. I think it was a European time frame, so it was one of the European conferences. And I really liked his focus on his experiences with applying ROS and just robotic systems in general in real world industrial applications, especially like really focused on the software side. And he has a long experience in working from the R&D department as well as the um, more research focused department. So without further ado, please welcome Matt Robinson and go ahead.
And I'll be remiss not to introduce my colleague, Tyler Marr, whose name is also on the slide here. Am I not sharing anymore, or is it, can you see my presentation slide?
Yes.
Okay. All right, we're good to go and we're recording. So thank you, Michael. Thanks, Tyler, for joining me. Thanks, everybody, for logging in. Immediately after your work day, I just finished dinner. So, anyways, let's hop to it. So, Tyler and I work at Southwest Research Institute. Southwest Research Institute's been down here in San Antonio, Texas, since 1947. Focused a lot on applied R&D. Right, so this little group is formed out of an intelligent systems division, getting into developing novel robotics applications. And so some other things that this institute down here in San Antonio is most known for are things like the Alvin submarine that discovered the Titanic, and of course, stewarding a lot of space missions, including New Horizons, which is noted here. We sit down here in a very sunny and hot in the summertime San Antonio on a pleasant 2,200 acres. And then Tyler and I sit right about here, although not right at this moment because we're home. But so anyways, the group here has been building custom industrial robotic systems since the early 80s. And there's a really interesting story about launching ROS-Industrial open source project, which was launched, and I'll touch on that in a little bit. And it was launched out of this group because of the nature of the robotics work they've been doing since the 80s. A little context about industrial robots, right? Sometimes when we think about industrial robots, we tend to think of the picture on the right. This wasn't so different even when I worked at Caterpillar. We had a number of different fabrication facilities. Normally the robots were just welding and doing the same kind of welding over and over again. So we would teach the robot and it would just like go and do that same thing over and over again. And that worked for a lot of cases, but you needed lots of stuff doing really the same thing and over again to justify the investment. Like I said, our team here got really into oddball robots. So you can see these are custom manipulators. This is one of our senior guys, Jeremy Zoss. He's still with us. This gentleman here is Daniel Solomon. He's now with Amazon Robotics. But this is basically a fighter jet surface finishing robotic system. It's got repurposed KUKA controllers and these custom manipulators. And we got asked to build these types of robots pretty regularly and still do. And most people have their favorite flavors of what color of robot they're using. And this really gave our team a lot of fits. And I ran into this problem during my time at Caterpillar too, where everyone wants to pick different hardware. Next thing you know, we're rewriting software all the time. And the difference in the hardware impacting the performance of our, just getting our algorithms to work the same and get the hardware to do what we need it to do was really challenging. And I'll touch a little bit more about that long history. Relative to industrial robot sales, you can see it's usually a lot of welding and material handling. You can see the uptick in material handling, no secret there, a lot of activity in machine vision going back over the few years. And the other good news is we're starting to see robots do some new things, which is interesting, but the uptick is slow. We talk about tools like OpenCV, we're talking about AMRs. Obviously, one thing that's led the advancement of some of these new things, sorry, I hit it the wrong way, is the evolution of ROS, right? So ROS has now been around 11 years or so, and it's really fostered a lot of innovation. Those people who are doing their labs at their universities are now getting out into industry and bringing those tools with them. And now at the point where they've been out in industry so long, they're actually part of the decision-making process. Back in my time at Caterpillar, we actually used a lot of ROS for prototyping and proof of concept. In some cases, we would end up deploying stuff without ROS, But even just if we used it for proof of concept and prototyping, we still got to sort of a place where we could move forward faster than if we didn't have it. The ecosystem was really nice, and it came with lots of different tools, and of course, the messaging. Moving forward, obviously, and I touched on industrial robots doing more. Obviously, today's talk, I'm going to talk a little bit more focus on ROS2, and there's a lot of different goals relative to ROS2. You know, there's this idea of solving some of the issues on the transport layer, and this is where DDS comes in, and leveraging something that's industry hard. Now, I know, for instance, when I go back to my industry time, we did a lot with OPC Way, Focus, what's another one, like Kepware, a lot of other different middlewares that are a little bit more object-oriented, where DDS is very data-centric, right? So it's been sort of a learning curve, both for a lot of people I interact with in industry, like they're like DDS and they're like, worried we're going to the dentist. So there's been some education here for industry, but we're trying to remind people like, hey, there's a long history of DDS being a very reliable foundation for lots of critical systems. I know we'd like to say security is built in. There's an avenue towards better security than what we're doing today. We do have to add some caveats there. Obviously, with the recent colonial news, it's like kind of very forward in the mind. We obviously are very interested in things like real time. There's a whole family and class of industrial applications that currently we cannot do very well with ROS-based approaches. You know, typically we still rely on sort of microcontroller strategies, and then, you know, rely on maybe pass stuff up to ROS at the higher order. But so we're hoping ROS2 actually enables a little bit richer interaction and process control down at where the action happens. So we're looking forward to that. And obviously the familiarity, though ROS2 is different, it's not so different, right? So we're very excited about supporting mass industrial adoption. And our goal and one of the missions of the ROS-Industrial Open Source Project is to leverage the benefit of open source for industry, right? Industry has a long time of silos, and those silos getting very tall and very thick walled and really stifling innovation, right? So we're hoping an open source presence in industry can foster more efficient, let's just say, innovation for all kinds of end users. So it's always good to define ROS-Industrial. As I noted, ROS-Industrial is an open source project. It really just seeks to extend ROS into sort of this industrial realm. ROS wasn't necessarily developed to do anything with industry, right? So there's been usually the very first ROS industrial repository was the Yaskawa driver repository that enabled ROS to sort of command a Yaskawa manipulator to move. And since then, we're kind of most known, our open source project is most known for the hardware faces for the industrial robots. Since then, though, one of our most trafficked repositories is the ROS plugin for Qt. So that's very broadly used for developers, particularly in the industrial sector. And of course, we do a lot and work with a lot of camera providers to provide supported drivers. A lot of them now, there's enough momentum in this space where it sort of just happens organically. A great example is Intel, for instance, in their RealSense line of cameras. But we've been approached by a number of different folks for, hey, what is expected for the performance and reliability relative to interfaces, and that's been great to support them. Another really important component is calibration for industrial. If I have a camera and I need my robot to see, I need to know exactly what the relationship is between the camera and the robot. So this is really enabling and core to a lot of the work we do. So this is the ROS Industrial Project in a nutshell. I'm going to kill the audio. I don't know if you guys can hear it anyway, but so these are just a number of different examples of ROS industrial, if you will, type applications, things that people have done with industrial manipulators, leveraging some of the different path planning capabilities, perception enabled path planning. This is, facilitating a lot of different things around inspection. Unstructured bin picking was a real hot space, definitely in the early years. And there's still some active development here. We're getting more into things like assembly high-speed sorting. So this was the original instantation of the core software that launched +1 robotics. High mix hazardous environment handling is very common. So this comes out of the nuclear robotics group at UT Austin. Adding different modalities of sensing in a more efficient way, right? So these are all just relevant examples. Human-robot collaboration is a very interesting space. And actually, we talk tonight, for those who kind of jumped on earlier, we talked about augmented reality, for instance, and some of the work that Lou Amadio and the Microsoft team are doing. And really that's actually just enabled another form of human robot interaction for industrial end users. It's of great interest. Confined space path planning is a big one, right? So we have a couple big initiatives there. Tyler's worked a lot in confined space path planning. Obviously, the application space is where we've done a lot of work with these sort of unstructured. The end user loves the idea of just throwing part in, no work holding, and the robot just finds it and does task X. And that's actually a real huge application space for ROS-Industrial as well. So I touched on it. It's been around since 2010. It's at where we work, but it was picked up by our unmanned ground systems group, and that's where it kind of got its start. Our industrial robot group caught wind of that and like, hey, this looks interesting. We're doing all these custom robots. They're a pain. So we camped out Sean Edwards, who was here in our department, and Yaskawa agreed to send us a free robot out to Willow Garage at the time. And they created this first instantation of ROS controlling an industrial manipulator. And then we did a follow-on kind of proof of concept project. Since then, we set up the repository, right? So there's a bunch of open source utilities out there at github.com/ROS-Industrial, github.com/ROS-Industrial Consortium. Have hyphens between all of those, the ROS-Industrial and ROS-Industrial Consortium, and focusing on sort of this realm of content. Since then, we've established a consortium because in the industrial space, there's a lot of nails, right? You can go hammer. Right, so which one do we go chase first, right? So this consortium's intent is to provide guidance to like, hey, what's important to you, industry people, and they talk about certain types of capability, classes of capability, easier ways for people to interact with robotic systems, and things like ease of use, right? So that's kind of like those are a lot of our charging initiatives. This is sort of a snapshot of the consortium membership. I recognize a few faces that are associated with some of our members, so thank you for supporting the ROS-Industrial open source project. But really we focus on some of these industrial mantras. Obviously the advanced capability makes for the awesome videos, but one thing that's been really enabling in recent years is this notion of interoperability. For those of us who've supported factories or stood up factories, the first factory I helped build from scratch down in Mexico, it was really nightmarish to share information from a robot to a laser cutter to a machining center. Like why can't they show the data? And then I have to like strip out all the data, put it in something like totally independent, and then I lose like a lot of the context of the data, right? So this interoperability component actually has been largely enabling for our industrial audience and has driven a lot of interest. But like lately also focusing on ease of use in human interface and reaction. And that's like I touched on the augmented reality as an example of that as well. More recently with the advent of ROS2, it's caused the ROS-Industrial kind of, if you will, technical leaders to sit around and think about, in industry, it's expected you buy some industrial widget. Like when I was at Caterpillar, I bought a robot. It was expected it would be in production for 10 years. So we've tried to think about, we have the first industrial deployment that my team supported was deployed in 2014. It's doing high mix painting in Wichita for aerospace. So the question is like, okay, if we make improvements to say core libraries, how can someone who's running something since 2014 take advantage of that? They're obviously not running Foxy. So we've really made a big push since about 2019 to try to build out all the core libraries, at least that we have sort of maintainership, and working with our partners or at Fraunhofer IPA and some of the other core maintainers of the ROS-Industrial, if you will, centric repositories, to do this where we can, where we provide a lot of capability that's ROS agnostic, and then offer up the ROS1 and ROS2 wrappers. So Yak is a common tool over in the ROS-Industrial GitHub, and you can go get Yak, and then of course you can get Yak ROS2, and that's something we've been trying to standardize around with some success. And there are of course edge cases where that's not possible, and you'll see where it's just package X ROS, package X ROS2 in that case. I want to touch on for again, like our industrial end users, we have to educate on the DDS. Like, why did you do this? What is this DDS thing? But it dates back, when one of my first jobs I worked in Navy nuclear and we encountered DDS, and this was back in 1995. And so it's definitely been around. It dates back to even the 70s. So for critical systems, particularly military applications. So long history, it's proven. We've just had to do, particularly on the industrial side, some education about what this is, right? So, you know, in industry, they're very comfortable with TCP/IP, things like Profinet and OPC-UA. So we play this role and kind of bridge the gap between the CS community, the CS robotics capability developing community, and these sort of traditional industrial folks. One of the more recent projects that kind of highlights the benefits of having a DDS in the loop was this recent project where we were working with, via the ARM Institute, working with Siemens and RTI, Southwest Research, Yaskawa, Kiba, and Schlumberger, where basically we had all these disparate machines of various vintages, and we had to kind of coordinate material process flows through them. Now, this is just sort of a cartoon, but it sort of tells the same story. There's a standard called MT-Connect, which provides a bunch of archetypes and basically data structures to manage what we call dynamic tasking. And so what we could do is we can actually enable an observational way for a machine to say, hey, I'm available, and then a certain robot can pair, right, to actually execute a task. Then they bind to do task execution. We demonstrated this workflow, or basically built out this orchestration as a native DDS application. And then it was able to interoperate with legacy machine tools, legacy ROS1 robots, which was the Kiba robot, ROS2 robots, and of course, at the time would be a UR, I think. And then the Yaskawa was obviously also another legacy ROS1 robot. And so we were able to have like basically OPC-UA devices, which were all the machine tools and conveyors, MT-Connect native devices, which was an old Mazak machining center, and then some other a mix of ROS1 and ROS2 devices, and they were all able to share information and collaborate. Some of this was enabled by the presence of DDS. And of course, the big output of this project was the DDS, the OPC-UA bridge, which you'll see here, this particular gateway. And then the nice thing is, in certain cases, if you're worried about ROS2 overhead, if for certain applications, you can instantiate them within, just say, the native DDS environment. That's actually what we did here. This orchestrator is the key enabler to basically facilitate all the collaboration. So it was a really interesting example of leveraging the DDS portion of the new ROS2 approach to realize a different level of capability and interoperability for an industrial use case. And okay, let's get into actual robots doing stuff in ROS2. The goal here is we had a client-funded project. This is sort of a, we'll just say, simplified representation of the client-funded robot. But the real idea here is back in 2019, the goal was, hey, ROS2 is getting pretty good. Hey, we've got this new project coming in to deliver some robots. Let's see what we can do. At the time, right, we had to be pretty creative on how we went about leveraging ROS2, because at the time there was no hardware interfaces. It was very slim pickings, right? So we had to think a little bit like, what do we do about the bridge? And at the time there was no Move It either. So fortunately, in the ROS industrial ecosystem, we provide a motion planning environment called Tesseract. Because it's sort of like fully in the purview of our team down in San Antonio, we were able to create a ROS2 variant of that. So then we really only had to worry about how we manage the bridge. And then, of course, these systems went into production. I guess, Tyler, I'm going to kick it over to you a little bit if you want to say a little bit about some of the insights and lessons learned on your experiences on this project.
Yeah, so basically, as Matt said at the time, especially, and still kind of to today, there's not really a whole bunch of driver support for hardware and stuff in ROS2. So that means you kind of have to use the bridge as is right now. So yeah, most of this planning and actual like smarts happening in ROS2. So I mentioned Tesseract, all the motion planning, that's all happening in ROS2. And then basically the final decisions are sent to ROS1, and like the UR or the KUKA in that instant is going to just execute the motion. So here's some just kind of experience or lessons learned from this project that Matt's referring to, and then also the Spirit project that I think we'll touch on a little bit more, the ARM Institute project. So basically the DDS client does matter. We found that certain implementations of DDS perform better than other ones. Certain ones are better at handling high frequency information, and then certain ones are better at ensuring that every single message you send gets there. And so we had some issues with that and choosing the clients and stuff. But one thing that I have since learned from talking to other people is that using component nodes is key, and that improves communication from nodes to nodes. So we hadn't been using component nodes at first because basically we were just treating it as a ROS1 system, but built in ROS2. So we just basically would use the exact same structure as a ROS1 node, just use all the syntax to make it ROS2. And so it sounds like using component nodes going forward will have better communication and maybe more reliability with the messaging across DDS. One thing I like that ROS2 provides is Python launch scripts. I know some people like to still use the XML, but I like having the handiness of being able to put in a bunch of like checks or different actual code in my launch scripts that I can kind of say, hey, I have a bunch of config files that I want to make sure they're exist on the system and that they're all the way up to date. And so I can just have those like YAML parsers at the beginning of the launch script and make sure those are all up to date and then actually launch the nodes. So I think that's pretty handy. One thing you can't do with the launch scripts though is pass command line commands to it very easily. So I know like with a lot of launch scripts, you'll have a bunch of flags like, oh, is this going to launch in simulation or not? And you can still pass those to the launch script, but they only can really be accessed in terms of passing the information to the node. You can't really access it very well inside the Python file itself. Let me see. Oh yeah, there's just another thing that I found interesting is so in ROS1, a lot of times you'll have like a service that triggers another service in your overall architecture. And I found it's a little bit trickier to do that in ROS2 due to the architecture of how it works. So basically, if you call a service and in that callback, you're trying to call another service, and both the callback, so the service client or service server and the service client are both running on the same ROS node instance, it won't be able to wait for the return. So a workaround for that is basically we found that whenever we're trying to in a node that we have as a service server and we know we're going to call other service clients, we make the clients actually so it'll be the same file, but the clients will be running on a separate ROS node than the server. And so that way it will allow you to wait for whenever you do service calls. And then one, I think, cool thing about using DDS is that you can easily talk to other systems. So at first we accidentally were talking to systems on our own network whenever we were first using ROS. So that was an interesting little bug to stumble upon. It would be running the robots and then somebody else would be running in simulation. And then all of a sudden we get this really weird behavior on the actual robot. And we'd like, in the simulation environment, we're suddenly seeing what the robot's actually doing. And like, oh wait, you have this ROS domain ID field that we need to make sure is unique on all of our systems. So it's convenient that you can easily access, you don't have to worry about setting up like the ROS IP and all of that stuff that you do with the ROS masters for communicating across systems. You just have this field set to the same and as an environment variable, and you can easily communicate. And then, yeah, it's really convenient to be able to do that. And then talking about the bridge works. I think the bridge works quite well. One thing it doesn't do super well is actions. And so you have to have a separate action bridge or a reverse action bridge, depending on where the action server lives. And so this can be a little tedious sometimes, especially with custom actions, which I had some experience doing. So you need to actually basically write a one-to-one correspondence in ROS1 and ROS2 for how each message is supposed to be translated from ROS1 to ROS2. And then there've been some occurrences where we've had communication issues where we'll send a request for an action to execute from ROS2, and it starts executing the action in ROS1, but the ROS2 side thinks it failed to execute. So that can be a little frustrating at times. But for the most part, we've had pretty good results with the ROS bridge.
Thanks, Tyler. We did get a question about what are component nodes. Thanks, Michael.
Yeah, so component nodes is kind of, so I'm not super familiar with it, as I have just kind of heard that that's what you should be using. I haven't really done it yet, but it's basically this new architecture design for in ROS2 to more efficiently utilize the communication infrastructure of DDS. And basically, from my really low understanding of it, it basically allows you to communicate the component nodes to communicate topics and messages without having to go through the full messaging pipeline in the same way that it would with like a regular full node communicating to each other. That I probably am wrong about exactly how it works, but it's just something new in ROS2, and it's a slightly different way of setting up the nodes, and supposedly it's much more efficient with communication.
There was also a question about, hey, you access command line arguments in your launch file using launch substitutions, but it's admitted it's more of a pain than it should be.
I'll have to look into that because I've been frustrated with that, but not frustrated enough to look into it too deeply. So that's good to know.
Right. So as Tyler alluded to, right, we have a program with in the Arm Institute with Spirit Aerosystems. They were the prime, and they were very interested in enabling operators to kind of work kind of in tandem with a robotic system. So leveraging a cobot, if you will, particularly UR10. And then we were like, hey, we're sticking with this ROS2 train, right? So we decided to do this fully open source. So when we submitted our proposal, we're like, hey, we want to open source the full application, right? So you can actually see it as a full application that's been implemented. Also, it does the same bridge, using the bridge at the time because the UR driver wasn't available. And so the idea was, as opposed to this huge honking industrial robot, they could go with this little cobot, and it works like 80-20, right? So the robot does sort of like the simple stuff, and you have this expert operator to do the detail work. Obviously, there was all these like considerations about, okay, yeah, the robot can bump into the person, but if it bumps into a person spinning something that's very painful, that's probably still a safety issue, but that was not our concern, that was the prime's concern. We can debate about whether this whole thing was even a smart idea. But the idea is like, okay, yep, here's what we're gonna do again, very similar to how Tyler described. This is probably very similar to the application you just described, Tyler, right? This sort of setup with the bridge, correct?
Yeah, exactly.
Right. We did leverage Gazebo to do some sensor emulation, in particular to do all the localization sort of testing and verification. And this also leverages the motion planning framework Tesseract, because again, when this project was launched, there was no Move It yet. So this is sort of how it's set up. Sorry. But basically Gazebo is really handy because it allowed us to do a lot of like sort of set up localization strategies. The goal was the end user would just randomly set up these parts in here. The system had to go find them. So localization is a big deal because they weren't going to consistently locate the parts in the cell. Also enabled a lot richer simulation of all the toolpath planning and the free motion planning. One of the other interesting things we've added is we have some other work that we've done. And this basically allows you to preview kind of like states for tools. Tyler, do you have a lot of experience with this, this particular implementation of this sort of view of the kind of
Yeah, so basically the idea here was, so also in this application, the robot's going to be on a rail, but the rail isn't like active, it's just a passive rail. And so they'll have the robot at one location, have it sand a bunch of the part, move it to a different location, have it sand a bunch of the part. So the idea here is we have waypoints all over the place, all over the part, and we just want to reach as many as we can from a given position. And so that's what you're seeing here is like the dark blue is all of your waypoints. The light blue are the ones that are unreachable. because they're either too far away or force you to be in a collision. And then the green, red, and yellow are, as you can see there, successfully planned or skipped or failed waypoints. So that's what the robot's actually going to execute. So this
right.
is just,
So it's a real,
I just added
view.
this to like give some more feedback to the users so they can understand kind of better what the robot's doing and thinking.
And this was originally part of the A5 program, right? But this is now its own separate open source
I think it was kind of inspired from some of that work, but this is what I wrote. But I'd seen stuff that other people had done and kind of took that as inspiration. So yeah,
no, right. These reach analysis tools are something that we've gotten great feedback from the industrial end users. And this is, typically A5, for those who don't know, is a mobile application where we allow operators to kind of drive it up next to a big airplane, right? But obviously they could just drive up to it. But ideally, if they get some view like this, they can kind of maybe tweak the position to get more. We call it a reachability preview. So Tyler, it's great that I thought maybe you borrowed some of that code, but no, that's cool. Thank you for pointing out to me. So one of the things Tyler worked on, compliance controller. You want to touch on this one, Tyler?
Yeah. So one of the things that we wanted to do in this application is it was kind of a low cost implementation. And so they wanted to do, rather than have a big, heavy, expensive compliance end effector, they wanted to do force control with just through the robot arm. So I was able to leverage some work that some other members of ROS-Industrial, the FCI over in Europe, they have this compliance controller package, which is above my head, to be honest, in terms of how the controls work, but basically allows you to do force control and position control at the same time. And so it basically creates kind of this pseudo force applied to the end effector of the end of the tip of the robot, and then the robot will move in that direction as if there's a force pulling it that direction. And so that force changes based off of where your target position is and what your target force you're applying is. I was able to leverage this to actually, so that first implementation is just to target towards one point. But I was able to build on this and use basically make a Cartesian trajectory. So it would actually follow a path and maintain a force and also maintain a speed, just using some like PID control for this. And so basically we were able to execute on the part a full trajectory at a controlled force and speed, which was kind of what the end result goal was to be.
Yeah, so for aerospace applications, right, when they're doing this processing on composite material, it's not just the force, it's not just the velocity, it is both that they have to adhere to. So that's kind of was an interesting development on there. There's a little video in the lab. I'll mute that one as well. So anyway, it just shows it running across. I think you actually do hold your phone down and get the screen too with the plotting, but maybe not in this one. So we have a video of it running on the actual deployment. Also in this project, the goal is that the operator could be like, yeah, robot, you didn't do such a great job. And they could circle the part and we would pick up the human markings and then truncate the prior planned paths within the region that it was observed. All right, so this is another novel, and there's a little bit of there's a repository here with the region detection. It's basically some OpenCV and then fitting it to the 3D data. But that's really nice feature. And then you supported some of the deployment integration. You want to share some of your integration experience?
Yeah. So, I mean, of course, you can see that those massive wires. That was one of the pain points. But yeah, in general, I would say this being a ROS2 system, things went quite well. I think I mentioned before we had that one issue of sometimes it wouldn't always catch that the action was accepted. And that was a little bit of a pain point. But for the most part, it was great working with the folks at Spirit, and say things went pretty smoothly, and we were able to get a demo system up and running and passed all the tests that they wanted to.
Yeah, so this is the nice video.
Yeah, so basically it's kind of like our scan and plan process that we like to do in a lot of systems. So the robot moves around and captures data on where the part is, point cloud data, so we can localize exactly where the part is. We have a bunch of pre-canned parts and tool paths for all the parts already. So once we localize it, we already have the tool path set up. And so at this point, once the user accepts that, yeah, that looks like that's where the part actually is, it does all the path planning. And so again, you can see here the dark blue waypoints that it's trying to reach to. And then, so also what it has to do in here is it's planning in 2 stages, because it figures out that there needs to be a media change in the middle, because the sanding paper only lasts for like 30 seconds of use. And so it has to do a media change at this point right there. And then it'll come back and do the rest of it.
And then here's your, is that done in plot juggler, this particular plot? Or
so this is multi-plot.
Okay.
I didn't know about plot juggler at this point, but yeah, so basically the green line is the force that it's applying on the surface. That's the interesting one. And the black line is what it's targeting.
The black is your target. Mm-hmm.
Yeah. And so one thing that we found is the UR doesn't have super precise force sensor. And obviously all that noise is, there's a ton of noise, but that's mainly coming from the sander, because there's a vibrating sander on the surface. So it's going to be pretty noisy.
It's orbital, random orbital.
Yeah. So I had to filter the data to make it look that clean. But in general, it was found that it was removing the material at an appropriate rate. And so that was pretty awesome to see it work and to see this system deployed. And so
I'll see if I can get the human, there's the end effector change out.
Yeah. So that end effector change out is just a UR canned program that it runs.
Right, because it goes to the same point every time.
Yeah.
So here's the operator. He's inspecting the part. He doesn't like these regions. So we get these sort of requests from our industry end users all the time, right? So in industry, there's a lot of interest in like, okay, well, what if everything didn't go off perfect? How can we trigger the system to make sure it's right? Obviously, with all the sensors, in this case, it's it's an Intel RealSense 435. It's just the Framos variant that's got the Ethernet IP interface and an industrial enclosure. But in this case, right, as opposed to like say just doing any other kind of verification or data logging, and they wanted this idea of the human being able to, the expert and operator, to be able to, yeah, this doesn't look right. And we have variations of this same kind of capability that you can do in RViz, right? So you can actually go with the mouse on the HMI for the cell, circle on the part, and it'll go and execute similarly, but they were very, but trust me, we debated, do we really have to use a marker on the part? And they're like, oh yes. So, but this is sort of how it's processing. And you notice there, it's just clipping those pre-trained paths. We do have another implementation where it actually replans inside the enclosed boundary. So a couple different variants of that.
Yeah, there's definitely some work that could have been done to like kind of make sure it more precisely covers all of the area, but it was pretty exciting. It took some tuning to get all of the OpenCV parameters right, so it recognized everything, but it's pretty exciting to see this actually sanding on those areas.
That was pretty cool. We did do some early implementation and testing with Move It 2 back then, right? So very in 2020, right? So we created this on that application, created this sort of early implementation of using Move It 2 within the industrial application. We do have a Move It maintainer on our team. So we try to make commitment, and then as it became, and we wanted to test it, we are currently doing some other evaluation of, say, the task constructor. There's actually on June 19th, there's ROS Developer Days. Jorge Nico will actually be talking about building out this sort of motion planning, use case using task constructors. So check that out. That's put on by the Construct. One of the things we've been doing is supporting, right? So one thing we do at the ROS-Industrial open source project is we heard all the cats, if you will. There's been all these questions about interfaces. Tyler touched on it. There was no UR driver, so we had to use the bridge. But we got Picnic, UR, FZI research together and formulated a plan. For those who are familiar with Picnic, they were kind of doing a lot of the work on ROS2 control, and they really wanted to showcase it on the UR. So they sort of had this burning use case. They originally reached out to us like, hey, we're just going to do this. Do you guys want to get involved? And I'm like, well, we can test, right? And we did do some testing, so we were involved in that context. But I'm like, hey, if we really want this to be sustained, because the nice thing is, one of the big things we advocate is that if there's going to be an interface for ROS, we want the OEMs to own it. For those who remember the Universal Robot interface from long ago, every time UR did a firmware update, the interface would go kaput, right? Because it was this open source project maintained by a bunch of developers, who knows where, right? Because it wasn't us. I think it was the guys over in Europe. So we eventually got UR on board. They basically created their actual client library. And then really the FZI research maintains this like little kind of add-on to basically leverage the action client library that UR offers to create the driver. So Picnic was going to go off and create their UR ROS2 interface. We're like, no, let's reach out to the tech lead over at UR in Europe and FZI research, who currently maintain the current ROS1 implementation, and see if we can create something that UR will actually maintain. And we got all that going, and that was, yes, right? Because like in the end, like, right, interfaces are only good is if the equipment provider plays ball, right, and maintains it, or else you end up with some library that's constantly not working. So that was really great outcomes. We were pretty excited for that. So, you know, as we like to say, ROS2 is ready for use. Tyler gave you some insights, what we learned, and they're delivering value, right? So, you know, Tyler, you're here. You're not actually babysitting broken robots on the shop floor. So, yeah, that's because they're running. So congratulations, all your hard work. But obviously, right, I mean, we had to make that choice. 2019, we had this big program. We took some risk, but at the same time, right, we get a lot of pushback from the industry membership. Like, hey, why am I going to use ROS2? Like, where's all the help? Where's all the documentation? Well, it's kind of a chicken egg thing, right? There's all this wealth and resource for ROS1 because people used it, right? So at some point, you just got to bite the bullet. You know, while we support and continue to help all of our stakeholders and people we work with ROS1, like, hey, your system, we're going to help you keep it running. We're doing what we can to make it easy to move to ROS2. To kind of like solve this chicken and egg issue. And we all got to throw a little skin in the game. That's the community, we can do this. And obviously we're trying to, what the crazy thing is, right, the universities that were providing this pipeline of kids coming out in industry that are dangerous with ROS, they're still, I was in a review. I sit on the technical advisory committee for ARM Institute. I was in a review, and here we are, what is it? May 2021. And they were like, yeah, like we're pushing these to the community for the ARM Institute. These are kinetic packages. I'm like, what? Right. So we are still working with academia to take a closer look at ROS2, right? And so we're trying to provide some resources. We provide training, for instance. We even have training all the way through Foxy, including up to some porting exercises and using the bridge. And it's all open source and free out there. We do guided training for our members, which a couple of you I think have attended. They're on the call today. But you know, we try to make these and do what we can to support resources to foster some uptake of ROS2, right? And here we go. The training link is there. And these are a number of the other different, I kind of mentioned the GitHub repos. You'll notice on my deck, which I'll send to Michael, right? I'll give you a PDF of this. And I cited a couple of the other interesting links there as well. But these are resources just available to the community. And with that, thanks. Tyler, any other closing comments? Did I kind of hit it? Or?
Yeah, no, in general, I'd say ROS2 is good. I like it. It's not a big transition or hard to transition from ROS1 to ROS2.
Awesome. Any other questions, comments, Michael?
I'll ask everyone for a question. I would like to ask a couple, but yeah, anybody, thanks for the talk. And please ask any questions.